Now I want to consider the honorable physics potato diagram. So we have some general extended object, and I want to calculate its total angular momentum. So I'm probably not going to be able to draw exactly that, but it sort of doesn't really matter. I have some crazy object here. I'm going to put a coordinate system down here. And this object is composed of a bunch of mass points. Let's just worry about in the plane. And, I don't know, maybe it's not uniform density, so maybe the center of mass is right there. So that's the center of mass. And I can use the coordinate RCM for the center of mass. And I would like to calculate, and let's say, the center of mass is moving around on some crazy trajectory, so it has some V center of mass. And furthermore, the object is rotating, let's say, in this direction. And so we want to calculate the total angular momentum with respect to this reference point, this chosen origin, which is fixed in an inertial frame. Okay? So the total should be the sum of all the individual R sub I cross P sub I. That is, angular momentum is a vector. It obeys the laws of vector addition. So if I have a bunch of constituent particles that together make up the whole body, I can just add up this property over all of them. Let me describe what I mean. Suppose I'm thinking now about this little patch of the extended object. So I could call R prime I the vector from the center of mass out to that little patch, whose mass I can call m sub I. And of course, the true and honest vector R from my chosen origin out to particle I would be like that. But our trick, like we've done before, is that we're going to go to the particle in two steps. First, passing via the center of mass. So we're going to express this R sub I as go first to the center of mass, and then do the correction from the center of mass, R prime sub I, in order to get out to particle I. So that's this term. What do I have to do for the momentum term? Can I factor m sub I out? Yeah, okay. So cross m sub I, and now I need v sub I. So that's v of the center of mass plus v prime sub I. Do you agree with that? That is, the position of particle I is what we wrote down here. The time derivative of that would give the velocity of particle I. And so I could either write this as R vector dot or v center of mass. Same story for this one. So we good? Okay, and now the challenge is going to be, how do I simplify this sum? And there's going to be a bunch of terms. So maybe I'll colonize the board over here. So L, the first term, sum on I, would be R center of mass cross m sub I v center of mass. Before I keep, maybe I'll keep writing out the four terms, and then we'll worry about how to simplify. Next, I could take R center of mass cross M sub I V prime sub I. So R CM cross M sub I V prime sub I. So this is going to be all within the summation. So R cross that one. Now I have to pick up this one. R prime I cross MI V center of mass. And lastly, R prime I cross MI V prime I. Okay. That's a mess. Luckily, some of these terms are going to die, or at least simplify. So on this one, the only term that is being summed over is the mass. This is a constant vector, that's a constant vector. Am I allowed to move a constant into the front? I mean, exchange the order of multiplication? That's all good. So, in fact, this whole sum is going to reduce to RCM cross capital M VCM, where capital M is the sum of all the masses. That's the total mass of the object. So that one's pretty straight ahead. In fact, just for grins, I can write that one as R center of mass cross P center of mass. And that turns out to be what we call the orbital angular momentum. Okay, next one. Any way to simplify this one? What's that? She says, I'm still summing over all the masses so I can get a big M. Well, but remember, it's the sum of that product and not, that doesn't pull apart. I could pull out RCM because that isn't changing in the sum. And so I could do, so let me call this term 2. Let me call this term 3. I'm going to pause on those, and then we'll come back. But this one, I think, is just every term depends on I. There's no way to simplify that one. This one is just going to be the sum over I of R prime I cross P prime I. That is, everything in that term is measured with respect to the center of mass. Okay, and this one, this fourth term is going to be called the spin angular momentum. There was a question or there was a hand up? Yeah. And so that term often will take the form I prime omega. I prime, the prime meaning that we're calculating with respect to the center of mass, times omega vector. Remember, we're using the right-hand rule to associate the direction of the angular velocity vector. Yes, question?
For the V prime I, can you actually interchange that with omega R? Or can you like use the equations for that?
This one?
Yeah. Can you use those equations?
Well,
because technically, if they're all spinning at omega, then you can simplify V into a term that is the same for all. Is the same for all I.
so I'm going to use that there, in fact, to get this, and we can go through that and be sure, but this is identical to a derivation that we already did last time. However, I'm not assuming, I really won't need to assume anything about whether this forms a rigid body. So I think we're pretty much good. Let me just see if we can motivate. What was the definition of the position of the center of mass? Way back when, this is like first week maybe? First moment divided by the sum of the masses or something like that? So the first moment with respect to R divided by M. That is to say the sum over all the masses, M sub I, times the position vector, R sub I, and then saying capital M meaning all of the mass. Well, multiply through by capital M, and we have M, R center of mass, is by definition, this is how we define the center of mass, the sum on I of M sub I, R prime sub I. This should be, careful, not so fast. This is R, vector R sub I. And now in order to make sense with, for instance, this expression, if I want to associate the M sub I with the R prime sub I, all I need to do is rewrite R sub I in terms of R prime sub I. So the definition from the diagram, if I add together RCM plus R prime I get the vector from the reference point out. So this is the same thing as summing over the mass M sub I, R prime I plus RCM. So what does that allow me to conclude? Well, okay, so let's keep simplifying. I can bust this apart into two sums. Sum on I, M sub I, R prime sub I, plus, well, wait a second. The only thing that's varying with I is M sub I in the second sum, so that's just all the mass, times RCM. So, light bulb? Jessica? No? So if M RCM is equal to M RCM plus this junk, that junk is 0. Okay, so I think I get to use that in this sum, because I could just shuffle the M sub I over to sit right next to the R prime sub I term, do that sum, and then cross it with the center of mass. But by this definition of the center of mass, the sum is 0. So that one's gone. But this one doesn't look the same. Sum number 2 doesn't have R sub I prime. So what am I going to do about that? Plug it in. Plug what in? A Glade air freshener? What? A Glade air freshener. Fresh out. Ain't got one. Are we stuck? Yeah? Make the same substitution. So, what's different between this sum and that one? Can I turn one of them trivially into the other? By doing what? Yeah, I just take a time derivative of this term. The masses aren't changing in time. I take a time derivative, and that turns R sub I prime into V sub I prime. which is in fact just what I have here. Time derivative of something that's always zero is zero. So this term dies an ignominious death. And we're left with an expression for the total angular momentum, L, which is equal to R center of mass cross P center of mass plus, well, I'll write it first as the sum on I of R prime I cross P prime I. But for a rigid body, this can be expressed as, I prime, I about the center of mass, times the angular velocity. Okay? So total is orbital plus spin.